Okay, we can start the presentation.
Okay. Hello, this is our mini project for the course SNS, Signals and Systems. The topic is adaptive noise suppression with transparency mix, and we have used software implementation for it. Our group was consists of Ninad, Karpe, Unmesh, Inamdar, and Dewang Joshi. That is me, and we are from Sardar Patel Institute of Technology. Our project focuses on developing a software-based transparency mode for earbuds and headphones. The idea is to mix program audio like music or calls with environmental sounds in real time, so users can stay aware of their surroundings without compromising audio quality. It's built entirely in software using Python for real-time signal processing. The three main goals are audio mixing, safety focus, and pure software. Traditional noise cancelling systems block all external sounds, which can be dangerous. For example, users might miss traffic noise or important announcements. Our goal was to find the optimal balance between immersion and awareness. Solution is a controlled pass-through system where ambient sounds are selectively mixed in. This ensures users remain safe and aware while still enjoying high-quality audio, essentially combining the benefits of noise cancellation and transparency in one balanced approach. Technically, the system is built on three pillars: filtering, level control, and a real time processing pipeline. We use a 101 tap FIR low pass filter with a 3500 Hz cutoff to remove harsh high frequencies while keeping clarity. Then we apply level control, boosting the main program audio by 1.4 times and reducing ambient audio to 0.2 times for an ideal mix. All processing happens at a 448 kHz sample rate using stereo channel handling for quality and real-time performance. Here's how the system processes sound. We start with the input stage, where two streams, program and ambient audio, are captured simultaneously. Next comes pre-processing, where the signals are resampled, aligned, and converted to stereo at 48 kHz. In the pre-processing core, FIR filtering and gain adjustments take place. Finally, the output stage performs safety clipping within the plus minus 1 range and writes out the final mixed audio, ensuring both clarity and safety compliance. At the signal processing level, we focus on two key aspects: filter design and level management. The FIR filter uses a Hamming window with a linear phase response, which helps preserve natural sound characteristics while removing unwanted highs. For level management, we precisely boost program audio by 40% and reduce ambient sound to 20%. The final mix is normalized and hard limited at plus minus 1 to prevent any clipping or distortion, ensuring a professional grade balanced output. This system is entirely Python based. The core language is Python 3.x, chosen for its flexibility and cross platform support. For computation, we use NumPy and SciPy. NumPy for numerical processing and SciPy for implementing the FIR filters and signal transformations. ResamPy handles sample rate conversion while SoundFile manages audio input output and multiple format support. Together, these libraries make the pipeline efficient, modular, and easy to adapt for real-time audio applications. Now, I would like to hand over to Ninad to continue with the presentation.
Hello. Now let's come to the results and the waveform analysis. I will switch to the code. So this is our Python code for our project Adaptive Noise Suppression with Transparency Bus. The aim of our project is to make a program audio that already contains ambient noise and adaptively remove or suppress the unwanted noise while keeping the speech or the main content clear and natural. The result is clean, transparent audio output that sounds balanced and distortion free. Let's see what each class of our code does. At the beginning, we have defined various parameters as explained in the yeah, explained by Devang earlier. Now let's move to the Biquad class. The Biquad class implements a Biquad filter, which is a basic digital filter used in audio processing. It can work as an high pass or low pass filter. In our project, it helps remove very low frequency hum or unwanted background components before the noise suppression stage, making the signal cleaner for further processing. The Softney expander. The Softney expander is a small noise reducer. It listens to the volume level of signal. When the sound is weak, like the background noise, it reduces it. When the speech or the main content is strong, it lets it pass. The soft knee makes the transition smooth, avoiding sudden volume drops, which helps our system sound natural instead of robotic. The safety limit. The safety limiter ensures the processed output never gets too loud or distorted. If the signal exceeds a safety level, it gently lowers the volume. This acts as a final protection layer, keeping our output clean and distortion free, even after heavy processing. The spectral kit. This is one of the most important parts of our project. The spectral gate performs a spectral noise suppression. It breaks the signal into small frames, converts each frame into frequency domain using FFT, and estimates what part of it is noise. Then it reduces those noise frequencies while keeping the desired parts, like speech, intact. This is one core of our adaptive noise suppression system. The delay line. Delay line is used to introduce a very small delay in samples to align the phase of different signals. It ensures that the processed and unprocessed signals stay in sync and don't cause echo or phasing effect, maintaining a clear and transparent output. The main function. Finally, the main function brings all together. It loads the noisy program audio, applies filtering, noise suppression, gain adjustment, and limiting, and then exports the final clean and transparent output file called processed mix. In summary, our project, Adaptive Noise Suppression with Transparency Mix, uses a chain of adaptive filters, expanders, spectral analysis to intelligently reduce the background noise while preserving the natural quality of the main audio. The final result is a clear, balanced, and professionally processed sound output. Now let's see practically how our code works. Here is an ambient.wave file where our ambient sound is stored. We have a program file which contains ambient as well as the
You should
other
hear
sounds.
steady noise soften, but alarms and
Now, as we run our Python code, we will see that a new
Hi,
file is
this is a
generated and
short demo
displayed
for software
automatically.
adaptive noise suppression with transparency mic. In this recording, the goal is to keep my voice clear while the background stays comfortable and natural. You should
We can see the difference clearly when we see the waveform of our sounds. We have plotted the waveform of the process mix and the program mix, and we can see the differences after processing. Now, I would like to hand over to Unmesh for further explanation.
Uh, right. Thank you, Ninad. Can we get the next slide, please? So this entire journey had many challenges. So some of the main challenges include first, over processing artifacts. Our initial attempts were too aggressive and created unwanted digital noise. The solution was to simplify our processing chain and sticking only to the essential components. Our second main hurdle was level balancing. Finding the perfect mix between the main program and the ambient sound was difficult. The solution came from extensive testing, which revealed a sweet spot ratio of 1.4x as explained by Dewang. The third problem was quality preservation. We found that an aggressive spectral gate we were using was actually harming the audio fidelity, as explained by Ninad. The entire solution was to modify it, which resulted in a much cleaner output. Finally, clipping prevention. We had to ensure the combined signal didn't overload and distort. The solution was to implement a hard safety clipping mechanism to keep the signal normalized. So our project has many real-world applications. Some of these real-world applications include consumer electronics as well as automotive and workplace uses. In consumer electronics, we can see that AirPods Pro transparency mode uses active noise cancellation. In automotive systems, it's perfect for mixing entertainment audio with crucial information like navigation, voice guidance, or safety alerts. And in workplace, it's incredibly useful for conference calls, allowing you to stay aware of your surroundings in an open office, or for remote workers who need to hear what's happening at home. The key learnings of our journey can be explained in this slide. First, we mastered the fundamentals of digital signal processing, particularly using Python audio libraries and implementing filter designs from scratch. We also gained real-world audio engineering experience, and the project reinforced the value of using a modular core architecture as explained by Ninad. But perhaps the most important takeaway was that the minimal processing often yields better quality. We discovered that critical precise parameter tuning and careful visual analysis of the audio are far more valuable than adding complex heavy-handed effects. So now I would like to conclude. Uh, we would say that this project is a definite success. We successfully implemented an adaptive transparency mix that provides clean, artifact-free audio processing. We achieved our goal of maintaining program quality while adding subtle, useful ambient awareness and reducing the amplitude of the input waveforms. The result is a professional grade output built on modular and extensible code, and personally, this project provided invaluable engineering experience. Thank you.